Spring potential energy. Spring potential energy has the following form. The amount of spring potential energy that a stretched or compressed spring has depends upon number one, the stiffness of the spring constant K, and also its displacement from equilibrium. What we'll do here at the beginning of the period is we'll incorporate spring potential energy now into situations involving energy conservation. Incorporate potential energy into energy conservation. Now, to arrive at an expression for conservation of energy involving the spring, we set up the easiest situation involving the spring, and that's for a simple harmonic oscillator that's horizontal. So the object will just oscillate back and forth on a horizontal frictionless surface. So we have a horizontal oscillator on a frictionless surface. Remember the basic picture associated with such a situation? It just looks like this. We have our wall or attachment, the spring itself, the mass attached to the spring, and then it oscillates back and forth. And now I haven't been demonstrating it as such. I've been demonstrating it with a vertical oscillator. A little bit later on today we'll be able to exactly see how we incorporate situations involving gravity and the spring force at the same time. But before we do, we deal with the horizontal case. Now, if I was going to apply the work energy theorem to this situation, as we did, by the way, back in chapter 7, the left-hand side of the expression would only be one thing in this case, and that's the work done by the spring force, because there's no friction in this situation, and neither the normal force nor gravity do any work. So the left-hand side of this equation is the work done by the spring force as the oscillation occurs. And then the work done by the spring force is the opposite of the work against the spring. This is what I went through quantitatively towards the end of class last time. And the work done against the spring is the change in spring potential energy as the object oscillates. So if you then take the spring potential energy term there and move it to the right-hand side of the expression, you end up now with your conservation equation. It looks exactly the same as it does when talking about situations with gravitational potential energy, now just spring potential energy. Okay, the left-hand side of the expression we still interpret as the change in total energy E of the object. If the change in the total energy E of the object is equal to 0, then the energy is conserved. Okay, no surprise at this point. You end up basically with the same expression when talking about spring potential energy as we did with gravitational potential energy. It's just we have now a slightly different mechanical form. Now, when we go through quantitative examples here, all that we have to do is fill in final minus initial for the various terms. We don't have to set up an integral any longer to calculate the work done by the spring force, because we now know the punchline that the spring potential energy and energy is conserved. So let's take a look at a basic example. Move on. It says spring semester begins. And what we'll do is we'll give this simple conceptual example here some numbers. And then we'll calculate out here in this first example a couple of basic things. so we faced this problem before involving the work energy theorem, but at this point we don't have to bother doing our work calculation because the energy is conserved. All right, so our situation is as follows here for part A. We'll begin with the spring stretched out like so from the equilibrium position. Okay, now we've got some numbers here. The mass attached is a kilogram, spring constant K, 10 newtons per meter. And then we stretch out the spring, this distance here, call it x equal to 0.5 meters, initially from the equilibrium position, and the object is then going to start from rest. And then what we want to calculate is the speed of the mass here as it passes through the equilibrium position. So then this little picture, that then looks like this. Here's our speed v. And now we just set up our conservation equation by then filling in all of the terms. No more dot product to do at this point. We just fill in everything respectively into the terms that we have on the right-hand side. Okay, first of all, the change in kinetic energy is the same as it was earlier when we were doing gravity problems. That is, we're going to have a final kinetic energy here with the speed v. That's 1/2 mv squared minus the initial kinetic energy of 0 because the object begins at rest. And now we've got our new term here, the change in spring potential energy. It's just the final value of 1/2 kx squared minus the initial value of 1/2 kx squared. So my final value of spring potential energy, notice, is going to be 0 because the object is passing through the equilibrium position here to end the problem. The spring is neither stretched nor compressed. So the final spring potential energy is 0. And then minus the initial spring potential energy, which occurs here when the spring was initially stretched out this distance x. So the initial spring potential energy is just 1/2 kx squared. And now all that we do is just simply solve for the speed v. So then algebraically, I have to do the following. I have to take this spring potential energy term here and move it to the left-hand side. I'll also toss away all of the zeros as I do. And I arrive at this equation here. And this equation here tells us exactly how the energy transforms in this process. So we begin up here at the top diagram, recall, with all spring potential energy. That's the left-hand side of my expression here. That then transforms or turns into the exact same amount of kinetic energy, like so, the right-hand side of the equation, as the mass passes through the equilibrium position. So very simply, this transforms or becomes this. Spring potential energy becomes kinetic energy. And now we just solve for the speed v. So when I solve for the speed v, the 1/2s do cancel each other out, but notice that neither the mass m nor the spring constant k cancel from each other. So to solve for the speed v, I have to divide the mass to the other side and then take the square root of both sides. After you do those couple of minor mathematical steps, the speed v ends up being the following expression. And now I just plug in my numbers. So first of all, the radical sign, we have the square root of 10 over 1, so the square root of 10. And then multiplied by the displacement here initially of 1/2 meter, and this turns out to be equal to 1.58 meters per second. Easy enough to calculate. Okay, then just to finish off in part B of the problem, it'll essentially be backwards. You could probably tell me the answer before I even set it up and solve the problem. That is, in part B, how far will the mass compress the spring on the other side of the equilibrium position? Yeah, it's obviously going to be 1/2 meter once again, showing that is easy to do. It's basically part A backwards. So now we'll picture part B in the following way. So we'll begin with the mass passing through the equilibrium position like so, with the speed now v0, the initial speed here for part B, equal to the 1.58 meters per second that we calculated a few minutes ago in part A. Okay, then what we have happen is the spring gets compressed like so. The object ends up at rest for an instant. And then the unknown here in part B of the problem is the distance x that we compress the spring. And then when I set up my conservation of energy equation, we'll essentially end up with the top board, except all of the terms will be backwards from each other. So setting it up from scratch. Okay, we first of all have our change in kinetic energy term. So in this case, the final kinetic energy is equal to 0 because the object ends up at rest, and then the initial kinetic energy depends upon the speed v naught. So final minus initial kinetic energy is as follows. And notice that it's just backwards of what we see for the change in kinetic energy term on the top board. And then similarly now for the change in potential energy. My final potential energy depends upon the unknown value of x that we're compressing the spring, minus the initial spring potential energy, which is 0, because the object is at the equilibrium position to begin part B of the problem. So final minus initial spring potential energy looks like this. And now we just solve for x. So to solve for x, just a little bit of algebra here first, move this negative term to the other side of the expression. It'll become positive, and I'll throw away all of the zeros as I do. That will then give me this equation here. And this expression here, notice, is the same thing as what we have up on the top board. It's just that the energy transformation in this case is backwards. All that happens here is that the kinetic energy that we have as we pass through equilibrium turns into spring potential energy as we compress the spring. Because the equation is the same as this one here, obviously if we solve for x, we would arrive at the same value, that is 0.5 meters. So describing a simple harmonic oscillator, as it's called by using conservation of energy, is pretty easy to do. Essentially what will happen here into the future is that as the oscillation occurs, it will always stretch out and compress the spring 0.5 meters from equilibrium. Every time it passes through the equilibrium position, it does so with a speed v of 1.58 meters per second. Easy enough. Yes, Zach?
Why is v equal to 0?
Okay, so for an instant, the object will end up at rest when it compresses the spring this maximum amount. That's the point in the oscillation that we're looking at. So usually with the conservation problems to begin with, we usually look at the end points of the oscillation and what happens as we pass through the equilibrium position. If we wanted to, we could examine some other point in the oscillation as well, but it's not really necessary for these basic examples. Now, as I've been demonstrating over and over here when talking about spring potential energy, I haven't been using a horizontal spring, but instead this vertical spring like so, just because it's really easy to show as a demonstration tool. But not only do we have changes in spring potential energy in a situation such as this, but we also have a change in height. We have a change in gravitational potential energy as well. So how do you arrive at a conservation equation when you have multiple forms of potential energy present? Actually, quite easily. Let me erase this first. So now, for the situation involving the vertical spring, we have multiple forms of potential energy present. How do we describe conservation of energy in such situations? And as I said, the example that we'll use here, and also in a couple of quantitative examples in just a few minutes, is the vertical spring. So in such situations, if I was going to apply the work energy theorem to this vertical oscillator, now in this case I'm going to have work done by two forces, gravity and the spring force. So my opening step, as is always the case here in chapters 7 and 8, is the work energy theorem, where on the left-hand side of the equation now for a vertical spring, we have two terms. We have the work done by the spring force, plus also the work done by gravity, because there is a height change here, like so. And then the work done by the spring force, like a few minutes ago in the horizontal situation, is the opposite of the work against the spring force. And similarly, the work done by gravity is the opposite of the work against gravity. And And then these work against terms are the respective changes in potential energy. So the first term here is the change in spring potential energy. This term here is the change in gravitational potential energy. And then if I just take those change in potential energy terms and move them to the right-hand side of the expression, no surprise, basically, you end up with the following conservation equation. It's just that in this expression here, we have two terms involving potential energy as opposed to one like we had earlier. This is, by the way, the basic form that conservation of energy always takes when you have multiple forms of potential energy present. You just essentially have additional terms as we go. So changes to chemical potential energy if necessary, etc. All that just gets tacked on repeatedly on the right-hand side of the expression. And then applying this equation for a couple of vertical spring problems, once you get the hang of it, is actually pretty easy to do. So I'll begin with an example that's similar to, say, a trampoline or like a jack-in-the-box toy from when you were a kid, not the rather horribly named restaurant. And I use the word restaurant rather loosely with regards to jack-in-the-box.
What would you call it?
I call it crap-in-the-box. Okay, so here's a version of a jack-in-the-box. Now, depending upon the problem, the mass could be attached to the spring, like it normally is, by the way, in the toy itself, or it doesn't necessarily have to be. So it just kind of depends upon the problem. There's a couple of variations. Now, all that's happening here initially is that a mass is compressing a spring vertically downwards, and then you just let go of it, like in the toy itself. And it does say so specifically in the problem that the mass is not attached to the spring. If it was, it's just a slightly different problem. Now, if you're having a little bit of trouble picturing this, it's just nothing more than the following. So let's say that right here is the spring's equilibrium position, and then right here is the mass like so, compressing the spring. And then we've got some numbers here, and I tried to match up the numbers realistically with what you would encounter in the toy itself. So the mass of the object, pretty small, 0.1 kilograms, that's 100 grams, like so. We're compressing at a pretty small distance here, x from the equilibrium position. That's 0.1 meters, that's about 10 centimeters. And then usually, if you recall from your own experience with the toy, the spring is usually pretty stiff, and I gave it a really large spring constant for that reason. So we'll say 500 newtons per meter for simplicity. And then what we do is we just let go of this object when it's initially at rest, like so. And then it will pass through the equilibrium position. When it does, the spring just ends up at rest at the equilibrium position, and the mass just continues upwards like so to some height that we ultimately want to find. Here it reaches some height such that for an instant the speed is 0. So it's basically like taking a marker and throwing it upwards like so, except we're just using a spring to do that. Okay, now what it asks for in the problem is this height here above the equilibrium position that the mass rises to. Let's refer to this here as h. And now we set up our conservation equation. When you set up the conservation equation, just treat each individual term separately from the others and ignore everything else as you go. So here's then what I mean by that. First of all, take a look at the change in kinetic energy term. Notice that this problem is unlike those that we faced thus far in the following sense. Both the initial kinetic energy and the final kinetic energy are zero because the object starts at rest and it ends up at rest. So the first term here, delta K, final minus initial kinetic energy, is actually 0 minus 0. Write it like that in your notes so you know exactly what it means later on when you do eventually review. Okay, then the next term is change in gravitational potential energy. Gravity has nothing to do with the spring. Ignore the spring completely. Just think of it like this. Let's say the object starts here at height 0. So if it starts at height 0, it has 0 gravitational potential energy. And then it ends up here at a total height, notice it's not just equal to h, but actually h plus x, like so, above the origin. So the final gravitational potential energy will be mg multiplied by that height. Once again, none of this has anything to do with the spring. We'll get to that in just a few minutes. So if we think of it as starting right here at the origin, its initial gravitational potential energy is 0, and then its final value is just mg multiplied by this total height change. So the final gravitational potential energy first, mg multiplied by that whole total height change, minus the initial, which is equal to 0, because we just start down at the origin. Okay, now we get to the spring potential energy term. Don't be fooled by the fact that it's vertical. We've already taken gravity into account in the previous term. Now all we have to do next is take into account changes in spring potential energy. My final spring potential energy is going to be 0, because the mass is not attached to the spring, and even though I haven't drawn it, the spring is just right here at the end of the problem, like so. So the final spring potential energy is just 0. The spring is neither stretched or compressed, it's just sitting here like that. And then minus the initial spring potential energy, which, as always, has to do with how far we're stretching, or in this case, compressing the spring from equilibrium. So then therefore, final minus initial spring potential energy just looks like this. So if you just kind of like isolate the terms in your mind, keep each individual term separate from each other, then analyzing each term is pretty easy to do with a little bit of basic practice. And now we just solve for h. So to solve for h, I'm just going to take this term here and move it to the other side algebraically. I'll throw away all of my zeros as I do. Like so. And notice that all of this expression is saying is that one form of potential energy becomes another. We start here at the beginning of the problem when all spring potential energy turns into the same amount of gravitational potential energy at the top at the end of the problem. It's as simple as that. And now we just solve for h. So to solve for h on the right-hand side, I'm going to do a little bit of distributing here first, like so. And it's just a little bit of math. And then to solve for h, subtract this mgx to the other side, and then I'll divide by mg here to get h by itself. So after you do these couple of minor mathematical steps, you end up with the following expression, and now I just plug in. So let's see, in the first term, 1/2 kx squared, that's 1/2 times 500 times 0.1 squared, then minus 0.1 times g times 0.1 again, and then all over mg, divided by 0.1 times 9.8. After all of that, it comes out to be, it's actually quite big. It's almost 2.5 meters, which is about 10 meters. So if you compress the spring initially and then just let it go, object rises to that height there above the equilibrium position. What would happen if we carry this problem into the future? Well, all that would happen now is that the mass would just drop back down onto the spring, compress it the exact same amount, 0.1 meters that we started with, and we basically would just do this over and over and over, rising to that height of 2.45 meters again, as long as there's no air resistance or friction. Any questions thus far? Okay, good. One last problem involving these vertical spring situations, and that is now specifically this vertical oscillator here that I've been using as a demonstration tool. Describing this oscillation vertically is actually pretty easy to do. Now with this example here, I'm not going to give the example any numbers. That's perfectly fine. I'm just going to describe it in variable form. And I can thoroughly demonstrate this problem as well. Let's see this slide right there. And as you'll see after I demonstrate the problem, the answer is actually intuitively obvious. Okay, so here's what happens. We first of all start off right here with the spring at its equilibrium position. It's neither stretched nor compressed. Okay, then I take my mass and attach it to the spring like so. And now I'm not going to drop it. I'm just going to lower the spring like so from its equilibrium position to this position here where the object ends up at rest once again. This is the distance d that is given in the problem. Okay, then I'll detach the mass and go back up to equilibrium like so, and then reattach. And now what I'm going to do is drop the object from rest, and then I'm going to catch it down on the bottom when it's at rest again for an instant prior to moving back upwards. That then looks like this, from here to here, like so. Let's refer to this distance here as x. This is our unknown. We want to figure out how big this x is in terms of d. Now, if you watch the process occur in sequence all at once, the answer is intuitively obvious. So we start here once again with the spring at equilibrium, attach the mass like so, and then lower it to this displacement here. Then raise it back up like this, and now I'm going to drop it from rest. And then right here is the distance x. How big do you suppose x is in terms of d? Yeah, it's twice as much. Showing it as such is actually pretty easy to do. So here's then how we go about doing this. We first of all have the spring here, initially at the equilibrium position like so for reference. And then as you saw me do, we first attach the mass to the spring and then lower it. And that then looks like this. Like so, where right here is the equilibrium position, and then the distance d, as is described in the problem, is this distance here. Now, the object is just sitting here at rest. The acceleration is equal to 0. There's no energy transformation that's occurring in this situation, and the object is just sitting there. But when it's just sitting there, the forces acting on it, spring force upwards and the object's weight downwards, they all just cancel each other out. So in terms of a simple force diagram, we have the object's weight, mg like so, and then the spring force upwards. Remember that the spring force is equal to the spring constant k multiplied by the displacement from equilibrium. That's just referred to as d here in the problem. So the spring force upwards is kd, and these two forces just cancel each other out. That is kd is equal to mg. Okay, then you saw me do the second process. So the second process is now to attach and then drop from rest. So then, right here to begin this process is the mass initially, here at the equilibrium position. And as you saw me do, I drop it from rest, and then I catch it when it's at rest at the bottom for an instant. That then looks like this. Like so. So when it's down here, it's at rest for an instant once again. This distance right here we'll refer to as x. This right here is the unknown. Okay, now, because there is a process of energy transfer in this second situation, that is when I drop the object from rest here and then catch it from rest here, the energy is conserved in this situation. So let me go ahead and set up my conservation of energy equation as is applied to this second scenario. So here's my conservation equation. And like in the last problem, all we do here is fill in our terms, but we think of each term separately. That's the easiest way to approach this equation initially. So first of all, the change in kinetic energy. Okay, like in the last example, the object started at rest and ended up at rest. So then therefore, the delta K, or change in kinetic energy term, is just 0 minus 0. And then we have the change in gravitational potential energy. Once again, don't be fooled by the spring. We'll take care of that in just a few minutes. But the only thing that matters when talking about gravity is the change in height. So let's just simply say that we end up down here at height 0, so the final gravitational potential energy is 0, and we begin up here at the height x above height 0. So then therefore, the initial gravitational potential energy will be mg multiplied by that height x. So the change in gravitational potential energy term will be the final minus the initial. Like so. Once again, this has nothing to do with the spring. Don't get confused by that. Okay, now we do in fact get the spring potential energy, which has nothing to do with height whatsoever. So then therefore, the final spring potential energy, as it always does, has to do with the displacement of the spring from its equilibrium position. So the final spring potential energy is just going to be 1/2 kx squared. The initial spring potential energy will be 0 as the object starts at equilibrium. Once again, none of this has to do with gravity. We already took that into account right here. So final minus initial spring potential energy looks like this. Okay, now if I just move this term here algebraically to the left-hand side and throw away all the zeros, I end up with this blue expression here. And all of this equation says, like in the jack-in-the-box problem a few minutes ago, is that one form of potential energy becomes another. The gravitational potential energy that we start with at the top of the diagram turns into the spring potential energy here at the bottom of the diagram as the object moves from here to here. And now, algebraically at this point, solving for the remainder of the problem is just a couple of minor steps, because basically what I end up with is now 2 equations and 2 unknowns. One of the unknowns is what I'm looking for, and that's the value of x. So I then therefore finish the problem in the following way. What I'm going to do is take this expression for mg, which is kd, just plug it right into here, like so. And now notice that a bunch of stuff cancels out. The spring constant k cancels from either side, as does one of the values of x, here. And then solve for the remaining value of x. Just take the 2 and move it to the other side, and then lo and behold, yes, the answer is in fact 2D. Basically what this problem is illustrating from an energy standpoint is the slight difference that there is between a vertical and horizontal oscillator. Here's how you can think of the difference. Okay, once again, right here is the equilibrium position. Notice that if I set the mass into oscillation, like so, it doesn't oscillate about the equilibrium position like it does for a horizontal oscillator. So then therefore, where does the object oscillate about? Well, if we go back up to equilibrium like so, attach the mass, and then lower it down the distance d right here, watch what happens when I now set this into oscillation, even with just a small amplitude. Notice that it's oscillating about this point. So instead of oscillating about the equilibrium position like a horizontal oscillator does, a vertical oscillator just oscillates about that point, that distance d that the mass hangs down vertically. That's the only difference between a vertical and horizontal oscillator. That's why I can use a vertical oscillator to demonstrate all of these situations. Okay? Well, let's take a short break there.
Take the waves. Just chill out. You got real,
You're legal.
Yeah, you are legal.
I'm what?
Physics team has that. That's up.
Tatum.
Say hi.
It's so weird. Being away on the beach.
So it oscillates about that point D as opposed to.
Stupid beach.
Talking about
So I can oscillate from that, so it wouldn't be any part of it. That distance is 2D. What that means is that if it was oscillating like that, the amplitude would oscillate just under D. D this
I did not see
way,
it
D
usually
this way.
specified.
They didn't call it.
I saw it. I can see Phil on.
I baked a cookie cake yesterday.
That sucks.
It was sugar free.
I love that movie.
I love that shit.
It was so good.
Thanks a little bit of bread.
I say like
Not really. No, she does. It's just that like every day.
So who's already gotten eliminated from Gotcha? Who's already claimed a victim from Gotcha? Now, if we find that other kids are cheating at the end of the period, I'll help you win. If I help you win, however, I get a cut of your winning.
Okay. How much? How much percent?
25%.
Okay.
You gotta haggle.
Because you know how people cheat?
No, I thought you were gonna
People
say.
cheat by like hanging around the classroom,
Yeah.
you know, like for like 5 minutes before the bell rings to try and get it. That's cheating. You can't do that. That's a violation of the rules.
Really? Okay.
So if I catch somebody doing that, like to try and sandbag somebody a year, I'm gonna help you escape.
Is it a safe zone?
All classrooms during class periods are safe zones, yes. Lunch and nutrition, I'm not sure of the rules exactly. I don't
So
know
how
how
would you
anything
help
goes
them?
inside the room.
How would you help
I've
them
seen her
escape?
before.
Well, don't forget I have a third door. It's a store.
You should have a walk.
Wait, what
Yeah,
if
I
you're
have
sick
third
that
I can't walk around under the.
Yeah, no, a lot of kids last year
Just
just didn't
stand
come to
out,
school for 3 months.
I feel like that we should.
Yeah, last year they had some issues. Some of the
So
kids
next,
received.
next week, take it.
One kid went to my friend's house and just waited, knocked on the door, was like, this is a mailman, and then he opened the door.
And when I get
It
to
takes place on campus.
the other grade.
No, but you can do it outside.
Yeah, you can do that.
Oh, you can? Okay.
That's why you see kids like-
On campus.
That's why you see kids like running to their cars.
Put it in the shredder.
I'm so screwed. I'm public
That
transit.
sounds good.
You're not safe on public road.
Yeah.
I can give you a
That's
ride.
the way I
Yeah,
thought.
baking crepes.
Why would
I thought it
you
was
do that?
only, you know, on campus during basketball.
Well, I can give you a ride to a spot.
The other time.
I can give you a ride to the bus that goes right by my house.
Just to get away from your
Yes, yeah, we talked a little bit
My
about that
dad
incident.
eats
is
it.
whether or
Right
not-
by
And my
that.
mom doesn't. She's the biggest fan of
Really?
chocolate.
Lucky you.
They were in the teacher locker.
Is it west or is
They're
it
getting hit by cars, like, oh my
What do you mean
gosh.
by west? She
down
lives
Venice or is it?
They took it a little too
Towards the
seriously.
beach?
upset now.
Yeah, that's, I didn't think they were
But
gonna.
there's like.
Damn, I really
We
I
talked
went
about
back
it.
to the yesterday, but at this place like time, so it was like really coordinated.
So disappointed in me right now.
I was like 8.
They like
Oh yeah, so and my sister showed me this flower.
It was better than the place.
I can
It was better than the place that we
rest.
And they have these like spicy rice noodle like wrapped up things.
See?
And I can't get
And
it.
then I'm gonna that. And then after that, it's like pie. It's gonna be a pumpkin pie with no crust.
And then after this was hella cheap. We had, you saw how much we had. It was $20.
I didn't.
And the
We ordered
oatmeal
probably
pancakes
7
have
dishes.
no flour. So,
$20.
oh my god, it's
So your duck can have flowers.
You have to be like,
Wait, what's the math? $3.
doesn't.
Alright, so moving on, don't worry, I will do one more break in a little while.
Yes. I don't want to bomb though.
Alright, so, if you've been paying close attention, and yes, you guys are a good class, you may have noticed that chapters 7 and 8 thus far is kind of falling into 2 parts. In the first part, basically chapter 7, we did the work energy theorem where we applied the work energy theorem to all the forces that we've seen, like a manual pushing force, kinetic friction, the spring force, gravity, blah, blah, blah. Now into chapter 8, kind of like as the second part of the process thus far, it looks like I've only been concentrating on 2 forces, the spring force and gravity, leading to situations involving conservation of energy. How do you incorporate into a description of conservation of energy the other types of forces, like a manual pushing force, or kinetic friction. When you do this, when you try to incorporate those forces into a description of energy conservation, you basically just end up with one equation. One equation to describe everything that we have done in chapters 7 and 8. So we kind of wrap everything together, if you will, into one expression. And now with this one expression, we can then treat all of our homework problems. And then, yes, the first exam for the second semester as well, which is on the horizon. I might as well make a note of it now. First exam of the second semester is a week from tomorrow. It is next Wednesday. Make a note of that if you have to right now. It's a week from Wednesday, okay? Right, so now how do we arrive at this one equation, if you will, to then describe everything that we've seen in the 2 chapters thus far? Well, what we have to do is we have to determine whether or not a manual pushing force and kinetic friction, see if those forces are conservative forces. The easiest way to describe this is just with a quantitative example. That's this example here. Take a moment to write that down. Now remember that the path is important when determining whether or not a force is conservative or not. You start and stop in the same position. Remember that's referred to as a closed path. Remember that the work done by gravity and the spring force in those situations was equal to 0, meaning that gravity and the spring force only transform kinetic energy into potential energy and then back again. They don't change the total energy of the object. We want to see if that's the case with these 2 other types of forces that we've seen, a manual pushing force and the force of kinetic friction. Now we're just going to keep the situation as easy as we can, and it's going to look a little silly. All that I'm going to do is take this stool and push it over a closed path like so. And remember that a closed path is that very merely I just start and stop in the same position. We're going to calculate the work done over the closed path by these 2 types of forces. Now, just to keep the picture as simple as possible, let's assume that regardless of where I am in the path, the force diagram always looks the same. Just think of it like this. So I'm going to push the stool horizontally like so, with a manual pushing force, F push of 20 newtons. We have the normal force and the stool's weight just canceling out, and equals mg. Mass of the stool is kind of large, however, 5 kilograms we'll say. And then opposing my motion always will be the force of kinetic friction, like so. Now, as I said, regardless of where I am in the path, let's just assume that geometrically it always looks the same. That is, I'm always pushing in the same direction that I am moving, like so, for simplicity. Yes, if we wanted to and set up a complicated integral, we could. I'm not going to bother. Let's just picture it like this. Now, let's just think of this as a distance. It's a total distance of 10 meters over which I push this object over the closed path. So 10 meters total over the closed path. And now I set up my simple work calculations from like early on in chapter 7. So let's calculate first the work done by F push. Now remember from the beginnings of chapter 7, that's the following dot product between F push and the displacement vector. If we're picturing the problem as simple as we're doing here, notice that F push and delta R are always in the same direction. There's always going to be a 0-degree angle between these 2 vectors. So this basically just ends up being force times distance. So mathematically it's easy enough. It's just 20 newtons multiplied by the total distance here of 10 meters. This then gives us a total of 200 joules. Now it's easy enough to calculate, but notice what it's not equal to. It's not equal to 0. So because it's not equal to 0, this then means that this non-conservative force, as it's called, is in fact changing the energy of the stool. The energy of the stool is not a constant. It's not a conserved quantity. Very simply, by me pushing on it with a non-conservative force, I add energy to the object itself. Now, we've already known that since the beginnings of chapter 7, but in the context of conservation of energy, it means that, yes, I am changing the energy of the stool. The energy of the stool is not a conserved quantity. So there is no potential energy term associated with a pushing force. So this non-conservative force, as it's called, adds energy to the object. The energy of the object is not a constant. So now, given that, you could probably guess a little bit ahead as to exactly what's going to happen with kinetic friction. So like early on in chapter 7, we would calculate the work done by kinetic friction by setting up the following dot product. Okay, as is always the case, there's a 180-degree angle between F sub k and the displacement. Cosine of 180 is equal to -1. So we pick up our negative sign as we always do. And then the force of kinetic friction is the coefficient multiplied by the normal force. The normal force is equal to the object's weight. So we end up with this little formula, as we've seen for the work done by kinetic friction in these horizontal situations. Easy enough. Okay, calculating it out. So let's see, I forgot to write it down on the top board, but the coefficient of kinetic friction was given to us in the problem as 0.3. So negative 0.3 times the mass of the stool, multiplied by g, times the total distance here, and this gives us negative 147 joules. Once again, easy enough to calculate, but notice, once again, that it's not equal to 0. So this non-conservative force is changing the energy of the stool. Obviously, it's removing energy from the stool. So non-conservative forces do not have potential energy associated with them. They do not transform kinetic energy into potential energy and then back again like the spring force and gravity. So these non-conservative forces change the energy of the object itself. The energy is not constant. So this non-conservative force removes energy from the object. So at this stage of the game, if you will, in work and energy, we basically have to recognize now that there are two broad categories of forces. Conservative forces, which have potential energy associated with them, and now non-conservative forces. And if we take into account these two types of forces, then we can in fact arrive at just one equation to describe everything that we've seen in the unit thus far. Before I do that, Henry, you had a question?
We didn't have a test on work, that was only on the final, right?
So specifically, the final exam that we had in the first semester was just on the work energy theorem and a little bit of the energy conservation that we did as far as we got into chapter 8. Now we're basically wrapping it all together here, the two chapters, 7 and 8, into one expression. And here's then how we come up with that one equation. For the entire unit. So as is always the case, we start with the work energy theorem. But as I said a moment ago, we now recognize that forces fall into two broad categories, non-conservative and conservative forces. So just in general, the left-hand side of the expression has to be thought of as the work done by any non-conservative forces that are present. This is, by the way, the notation that you'll usually see. Plus the work done by conservative forces that are present, such as gravity and the spring force. Okay, now in terms of my next step here of the mathematical process, the work done by conservative forces, remember, is the opposite of the work against, which is then equal to the change in the various forms of potential energy. So this term right here, when talking about the spring force and gravity, is equal to the following. The opposite of the change in spring potential energy and the opposite of the change in gravitational potential energy. And then if I take those two potential energy terms and then move them to the right-hand side of the expression, this is then when we arrive at our one equation to describe the entire two chapters thus far. That would then be the following. The work done by non-conservative forces is equal to the change in kinetic energy plus the change in the various forms of potential energy that we've seen. Now, the left-hand side of the equation is still the same thing as it always is. It's a change in the total energy E of the object. And now there's basically three possibilities. If there are no non-conservative forces present, like early on in Chapter 8, then you just simply have the following. That is, if the work done by non-conservative forces is equal to 0, then the change in the total energy E of the object is equal to 0. So the energy is conserved. The final amount of energy and the initial amount of energies are the same. That's like earlier today, for example, when talking about spring potential energy. And then it's also possible that if you push on something, that the work done by the non-conservative force is a positive number. This then means that the change in the total energy E of the object is a positive number. And then change, remember, is final minus initial. So then therefore the final energy would have to be greater than the initial energy if the change in the energy is a positive number. And then the last situation is like what happens if you have kinetic friction. That is, if the work done by the non-conservative force is negative, it's less than 0, then the change in the total energy E of the object is less than 0. So the final energy is less than the initial energy. Remember, that change is final minus initial. If the change is a negative number, then the final energy is less than the initial energy. Energy was taken away by the force. As simple as that. So everything that we've seen in the 2 chapters is now wrapped up into this one equation. And then the last thing to do is just apply it to some simple situations, and that's it. So eventually, when it does come to the homework, the web assignment is due at the end of the week, and it's due at its normal time, remember. Hopefully you've gotten a start on it. And then eventually, when we do get to the exam, first exam of the second semester, we can just apply the equation. So the last thing to do with it is just practice it for a couple of problems. Yes?
Can we attempt all the websites now?
Yes, yeah, you can do all the website. Okay. Let's try this. Now, most of the time, by the way, in problems specifically on non-conservative forces, the non-conservative force is usually kinetic friction. Every now and then you may see a manual pushing force, but for the most part, the non-conservative force is kinetic friction. Yes, lots of deep breaths. All right, so how do we treat this situation now, as we've seen, as a combination of the stuff that we have seen thus far, that is into one shot, one expression. So here's our setup. This is, by the way, finally the last time you'll see the incline, by the way. Thank God. Okay, so we have our 30-degree angle to keep things easy. Okay, we've got a little bit of kinetic friction here. The coefficient is 0.3. And right here is our object initially at rest. V naught is equal to 0. And then slides down to the bottom like so. Ends up with a speed v that we have to calculate. Now as it does so, it undergoes a height change here, h, which is given as 1 meter in the example. But there's also, remember, some kinetic friction here. So we do need to know the total displacement over which friction acts. That's the hypotenuse of this triangle. We do need to know what the hypotenuse is equal to. So before I do anything else in the problem, let's just do a little bit of trig here and figure out what the hypotenuse is. So the sine of the angle is equal to the opposite side over the hypotenuse like so. If you do a little bit of cross multiplying here, the hypotenuse is the opposite side, h, divided by the sine of the angle. Now mathematically, this is straightforward. We just have 1 meter divided by the sine of 30. Sine of 30 is a half. This just equals 2 meters. So we have to do a little bit of trick here first before we set up the problem. And now just essentially in one shot, if you will, here is then our equation. We're going to have work done by, first of all, kinetic friction, our non-conservative force, that then equals the change in kinetic energy plus change in gravitational potential energy. There's no spring in this problem, so then therefore ignore the spring potential energy term completely. We just have this expression here to work with. And now we do a combination of the things that we've done in this unit thus far. Let's just fill in all the terms on the right-hand side first, like we would have in conservation of energy situations earlier. So first of all, change in kinetic energy. We'll have a final kinetic energy here, 1/2 mv squared, minus the initial kinetic energy of 0. And then the next term is change in gravitational potential energy. We'll end up down here at the bottom. Final gravitational potential energy is 0. Start up there at the top. The initial is mgh. So final minus initial, like so. But then we get to our work calculation on the left-hand side. When it comes to the work calculation on the left-hand side, you have to do the dot product. You have to do the correct work in calculating the work done by friction. It's unavoidable. Once we have that, however, we just stick it into here and then solve for the speed v. So remember how this problem works out. Nice little bit of review here in the second semester. As the object slides down the hill, we have the following force diagram. Normal force perpendicular to the slope. Force of gravity straight downwards, and then because our displacement delta r is down the slope, the force of kinetic friction opposes that like so, pointing up the slope. We break mg into its usual components, here and here, showing once again the angle theta. And then we set up our dot product in the following way. This is unavoidable, as I said, when calculating the work done by this non-conservative force. We have, first of all, as always, our 180-degree angle between the two vectors. Cosine of 180 is equal to -1. So we pick up our negative sign as always. And then the force of kinetic friction is the coefficient multiplied by the normal force. Remember that the normal force here is being exactly canceled out by the mg cosine theta component right here. So this guy right here is coefficient times normal force, like so. Once again, we've seen this before. And that term then gets plugged in here into the left-hand side, and then we just solve for our speed v. So plugging up into the left-hand side, so, and then the right-hand side, we have our other stuff. Throwing away like zeros. So, and now we just solve for the speed v. So notice that to solve for the speed v, I need both h and delta r. That's why I did the delta r calculation on the top board initially before I began the problem. Okay, just finishing up. Let's move the mgh here to the other side, like so. Times delta r. There we go. And then the last couple of minor steps here is to first of all cancel the mass from each term. Here, here, here. Multiply by 2 on both sides and then take the square root. So doing those couple of steps like so gives us this rather ugly looking mess. And then we just plug in and finish. So working my way through the parentheses first. Let's see, 9.8 times 1 for h. Then minus 0.3 times g times cosine of 30 times 2 meters for delta r, multiplied by 2 here, and then square root the whole thing. And then after all that, finally, it ends up being 3.07 per second. So once again, note that essentially what we've done here with this problem, and then just 2 more to finish up, is combine everything that we've seen thus far in 2 units into one equation. How about a second break right here? How's that sound? Sure.
No.
It's not that bad.
It looks much too fast.
They only make PSCs. What's the horsepower? How are you okay? You can shred it. You get a custom match. I'll say about my bucket shit. You should get it. Which I'm not helping myself. Does have to be the sickest fucking reason. Does it have to be factory? Or will they keep your other modifications? Or will you pick, because what is going to be done is that they'll set, they can have a factory and they'll ship it to one of their like actual certified tuners. Because they're doing BMW has their own tuning post, so they can do their own tuning post. You can put like really good sway ball drivers, like an extra turbo, like an upgraded turbo. Race king wheels.
Did you go to City Hall today? Because you were on my roster, right? Yeah.
We got to go all the way to the top.
All the way to the top. You know that building was destroyed by the Martians in World War.
Yeah, I know that. I know that.
I don't know when they rebuilt it.
But they did, they won't.
I can see City Hall.
Is that the tallest building?
Because I live on a small hill in Rose Beach. I can see all the way out across the city.
I feel like it's.
That one, okay.
But what you can do is you can like take the upgraded one on yourself and save your life. I do long runs.
All right, before I start again and finish up here, let me show you a nice little demonstration before we go any further. Okay, so take a look at this little object right here. What I'm going to do is take this little object, it's called a popper, by the way. I'm going to fold it like so. And then what I'm going to do is just hold it at some height here above the floor and then watch what happens. Notice it rose.
Yeah.
Notice it rose to a greater height than where I started. So watch it again. Fold it like so. Hold it here. Drop it. Then it rises to this greater height that I dropped it from. So initially, it looks like I violated conservation of energy. Then I started with some gravitational potential energy here, but ended up with more gravitational potential energy when the object rose to this greater height. So it looks like that somehow energy was created in this process. Who could explain, however, how this really works? When I just simply do this and then drop it like so. Yes?
Put more potential energy in it when you bend it.
Okay, so when I bend it, what is this analogous to? What other form of potential energy have we seen?
Spring.
Yeah, it's kind of like a spring potential energy. So I give it a little bit of spring potential energy by doing this like so. So when I hold it here at this height, it actually has two types of potential energy. It has spring potential energy and gravitational potential energy. And then when it hits the floor and pops, like so, then that spring potential energy is like tripped, if you will. It's like releasing a spring, and then it rises to a greater height because now all of the energy is gravitational potential energy. So the difference in the two gravitational potential energies, the lesser value here that I dropped it from, and the greater value here, that difference in gravitational potential energy right there is exactly equal to the spring potential energy that I give this in doing work and folding it in the first place like so, and then gets stripped it in a manner with this little popper, okay? This little guy is kind of cute. Okay?
Charlie, you ever pop it on your hand?
Sure, you can pop it on your forehead if you want.
So have you ever done
The
this?
spring constant of this thing actually is kind of large. I mean, this is kind of like, like taking a racquetball and cutting it in half. So the rubber is actually pretty stiff. When you do something like this. I actually have the regular students do a short little lab where they measure the spring constant here. It's in the neighborhood of about 100 newtons per meter. So even though it doesn't seem like much, this is kind of like acting like a stiff spring. So it actually kind of hurts if you bump it against your head. You could try that if you want to in a period. All right, let me go ahead and finish up now this section on non-conservative forces with 2 examples that'll take us towards the end of the period. Remember that the period is a little bit shorter today. The period ends at like 1:50 or so, something like that. Remember that. All right, so earlier today, we did conservation of energy, of course, with spring potential energy. But now what happens if you have a spring situation with the non-conservative force of friction also taken into account? I'm sorry, Nathan, you were about to say something?
Yeah, you say this was the last example?
2 more, this one and one more, finish off. And then when it comes to these last 3 problems, what I did a few minutes ago, this one and then one more as a follow-up. If you understand these 3 problems, not just conceptually, but also mathematically as well, then you pretty much have the 2 chapters down pretty well. Now notice how the problem is phrased. We're compressing the spring initially 0.5 meters from equilibrium, release the mass from rest, stretches out the spring on the other side of the equilibrium position. But because there's kinetic friction, is it still going to stretch out the spring the original distance of 0.5 meters? No, it's obviously going to be a little bit less because some of the energy is getting lost as it is. So then, here's how we approach the example. Here's the little picture that goes with it. So we begin by compressing the spring like so. So here's the equilibrium position as always. We'll begin with the mass here initially at rest. And now we've got the following numbers. Okay, first of all, the mass itself, just a kilogram. Spring constant K, maybe kind of big in this case, 100 newtons per meter. And then right here is the original displacement from equilibrium, x of 0.5 meters. But now, we've got a little bit of kinetic friction. Coefficient of kinetic friction is 0.3. So then when we end the problem, the mass will stretch out the spring like so from the equilibrium position. The mass will once again come to rest. And now we're going to have here an unknown value that we stretched out the spring. We're expecting it to be different than the original value of x. So I'm going to give this a different name. I'm going to call it x prime. That is our unknown like so. Okay, now here's our basic expression to set up. We're going to have the work done by kinetic friction or non-conservative force, and then the right-hand side is going to be change in kinetic energy plus change in spring potential energy. There's no change in height in this problem, so don't even bother with a change in gravitational potential energy term. Okay, now we start by just filling in the terms on the right-hand side of the expression. Notice immediately, like a couple of the problems that we've done here today thus far, that both the initial and final kinetic energies are 0. The object starts and ends up at rest. So the first term is 0 minus 0. Once again, write it as such in your notes. Okay, then we have change in spring potential energy. Our final spring potential energy has to do with how far we're stretching out the spring here to end. So the final spring potential energy, 1/2 kx prime squared, minus then the initial spring potential energy, which depends upon how we're initially compressing the spring the distance x. So So the initial spring potential energy is 1/2 kx squared. Now, if this was a frictionless case, if the left-hand side of the expression was equal to 0, then obviously x prime and x are the exact same thing. But not so in this case because we do have kinetic friction. Now, how do we deal with this work calculation here? Well, we just set up our force diagram and calculate the work done by friction with our dot product. When I set up my force diagram, however, I'm going to ignore the spring force. The reason why is because I've already taken into account here with change in spring potential energy. So it's already been dealt with, I don't at the bottom. So as the object slides from left to right in this problem, we just have the following forces other than the spring force acting on it. We have the normal force, gravity, cancel each other out. And then opposing the motion, which is to the right-hand side, we have the force of kinetic friction, like so, pointing to the left-hand side, right here. Now this is just like the stool problem from a few minutes ago. It's a horizontal problem. So the work done by kinetic friction here is exactly the same formula as it was in that example from earlier. This expression here. The negative sign comes from the cosine of 180 degrees between the vectors. The force of kinetic friction itself, S of k, is the coefficient multiplied by the normal force. So same stuff that we've seen here in a number of other examples. However, what is the displacement delta R equal to in the context of this problem? That is the total displacement over which the friction acts. What is it also equal to in terms of the variables here on the diagrams above?
X plus X prime.
Yeah, it's x plus x prime. We have to take that into account, of course. That right there is going to be the work done by kinetic friction. And then this term here, which gets plugged up into the left-hand side of the equation, and then I just have to solve for x prime. Okay, now this is where the groans are going to come in, because if you look at the expression carefully, then I have to solve for x prime. Unfortunately, what am I going to have to use to solve for x prime?
Quadratic formula.
Yeah, it's quadratic.
Calculator.
See, that's where the groans start. I hate to say it, that's usually the case when you have a spring and friction at the same time. If you're solving for a displacement, it's usually quadratic formula. All right, so here's then how this is going to work. First of all, what I'm going to do is distribute the terms here on the left. That will give me this. Like so. And then I've got these guys here on the right-hand side. I can get rid of the zero, of course. We have these guys here on the right-hand side, like so. And then once again, I'm solving here for x prime. So to solve for x prime, I'm going to take these two terms here, move them to the right-hand side. And when I do, here's what I get. First of all, there's this term here. And then I'm going to move this guy to the other side. That gives me this. And then I'm going to move this guy to the other side as well. That gives me this. So take a look at this carefully. Okay, now why did I write things here the way I did? Well, remember that x is known. We know the x right here and here, for example, is 0.5 meters. X prime is the unknown. So then, therefore, our coefficients for the quadratic formula are going to be as follows. Right here is going to be the coefficient A. Right here is the coefficient B. And this whole thing, this is why I use parentheses. This whole thing there, all the constants, that's the coefficient C. And now I just plug everything in. So solving for x prime, I first of all have negative B, like so. Plus or minus, two answers somehow, so I got to figure out which is the correct answer. And then square root of first B squared minus 4 times A times C. All over 2A. It's a god-awful mess, as you can see. Let me me just check myself. B squared 4AC, good. All over 2A. Okay, now it simplifies a little bit with B. 2's canceled here, big deal. 2 cancels here and here, thereby making this 2. Now let's see what we get. All right, so solving here for x prime, let me now go ahead and plug in my stuff, and let's see what we obtain. Okay, so first of all, coefficient mg. So 0.3 times 1 times 9.8. 0.3 times 1 times 9.8. So this is negative 2.94, plus or minus. Okay, so b squared, good, minus 2 times k is 100 times quantity, coefficient mgx. Coefficient mgx minus 1/2 times k times x squared. Square root that. Good. And then all over in the denominator k, 100. Okay, now, notice that one of the answers will be negative if I choose the negative sign, for example, here in the numerator of the expression. Throw that answer out immediately. The reason why we do is because remember that buried in all of this is dot products. And dot products always give you magnitudes. So x prime is not a position vector. It's a distance. It's a magnitude. So the negative answer literally has no physical meaning. It's what's called a mathematical artifact. You just toss it out. So then therefore, for that reason, I'm going to choose the plus sign here in the numerator of the expression. That'll give me a positive value for x prime, and that's what I should obtain. So then therefore, we have negative 2.94 plus 47.06 all over 100. When I do this, I end up with something that is very reasonable. I end up with 0.44 meters. Notice that that is in fact a little bit less than 0.5 meters because yes, some of the energy has been lost as heat. So in the first of these non-conservative force examples, we had friction with a change in height. In the second one, we had friction with a spring. What if you have everything all at once in one single example? We'll use that to finish this off for the day. That's this one here.
With kinetic energy, if it's not 0 minus 0, you know how to take 1/2 k, what's it?
So then you would have a 1/2 mv squared minus 0 because it did start at rest. Another variant of this problem that we could do if we wanted would be to figure out the speed v as it passes through the equilibrium position. However, we would still have to take kinetic friction into account when we do. It's just another example.
Okay. But it is 1/2 mv.
Yeah. So we can do variations ad infinitum of these examples, or at least as far as we can go, as far as we can stomach. It's usually, by the way, at this point, of course, in the lecture, at this point in the unit, that I'm kind of starting to run out of things to say. There's only so much we can do with this. So the last of these examples then is just to combine everything all at once. You don't want this to happen to you, by the way. It's survivable, but it wouldn't be pleasant. Incidentally, elevators are very safe. If you go into an elevator in a really tall office building or something like that, particularly modern buildings that have been built within the last few decades or so, you're frankly in actually greater danger going back and forth from your house to the building than you are when you're actually in the elevator itself. So elevators are actually quite safe. But should there be a catastrophic incident, there are some safety features that are built into the elevator. That's what's being described here. It basically falls into two parts. If some sort of catastrophic event happens where the cable on the elevator snaps, as is described here in this problem, usually what that will do is it will mechanically trip some sort of braking system. like as the elevator is sliding downwards on the rails, the elevator cab that is, some sort of mechanical braking system will get tripped. That's the kinetic frictional force of 1,000 pounds described here in the problem. And then down at the bottom of the elevator shaft itself is usually some sort of assembly of cushioning springs. Those springs are there to try to damp out as much of the energy as possible, thereby basically making the situation survivable if the accident happens at a relatively low altitude above the floor of the elevator shaft itself. Now this is kind of like the jack-in-the-box problem from earlier in the day today, just a little bit backwards, and we also take into account kinetic friction. But here's then how it works out. Okay, first of all, we start with the elevator up here. And notice, by the way, it's an English units problem. We're given that the weight of the elevator, mg, is 4,000 pounds. These are all, by the way, realistic numbers. Okay, then right here is the equilibrium position of this cushioning spring, like so. The spring itself usually has a pretty big spring constant. This is also a reasonable number, 10,000 pounds per foot. Okay, then the elevator is here, this height h above the spring. That's the distance of 12 feet. That's basically a single story that is given here in the example. And then as the object slides downwards on the rails, if you will, of the elevator shaft itself, there's a force of kinetic friction opposing the motion, given to us as a number. It's 1,000 pounds. Okay, now we're going to drop the elevator from rest like so, and then ends up compressing the spring some distance where it will eventually come to rest again for an instant. What happens afterwards we don't care about, but then as the problem ends, here's our elevator like so, compressing the spring where it ends up at rest for an instant, and then right here is the unknown in the problem, and that's the distance x. So as I said, if you draw it out in this manner, it's kind of like the jack-in-the-box problem from earlier backwards, except we're now also going to take into account kinetic friction. Okay, this problem has basically everything in it, in the sense that we're going to have work done by our non-conservative force here, kinetic friction, resulting then in the change in kinetic energy, plus change in gravitational potential energy, plus change in the spring potential energy. So we basically have everything here in the example. Okay, now on the right-hand side, we fill in our terms, like the other problems that we've seen here today. Object starts at rest, ends up at rest, so the change in kinetic energy term is 0 minus 0. Okay, next we get to gravity. Once again, gravity has nothing to do with the spring. Ignore the spring completely. So let's just say that we end up here at height 0 to end the problem. So the final gravitational potential energy will be 0. The initial has to do when we're this height here to start the problem. Notice that the total height, however, above our origin for gravity is going to be h plus x. So then therefore, final minus initial gravitational potential energy looks like this. Once again, it has nothing to do with the spring. We just look at change in height. Okay, now we do get to the change in spring potential energy. Notice that when we end the problem, we're compressing the spring this distance x from equilibrium methods. So the final spring potential energy is 1/2 kx squared. The initial spring potential energy is 0. The elevator is nowhere near the spring, and the spring is just at its equilibrium position. So final minus initial spring potential energy looks like this. Then we get to the left-hand side, which is the work done by friction. So how do we picture friction in this problem? Well, as the elevator is sliding downwards, in which direction must kinetic friction act? Upwards, like so. So here's the force of kinetic friction like so, in the opposite direction of our displacement. As is always the case, we have a 180-degree angle here between those two vectors. So when we calculate the work done by kinetic friction, as is always the case, we'll pick up a negative sign here from the cosine of 180. Now there's one more minor step that I have to do here prior to plugging this expression into the left-hand side of my overall equation, and that's just to describe the displacement delta r. What is the delta r equal to in terms of my diagrams here? That is the total displacement over which the friction acts.
H plus K.
It's h plus x, that's right. So you gotta be careful of that in a problem such as this. This is then what goes here on the left-hand side of the equation. And now we have to take this expression here and solve it for x. Notice that it's once again gonna be a quadratic formula in solving for x. That's usually the case when you have the spring and friction taken into account, and you're looking for the distance that the spring is stretched or compressed. It's usually quadratic formula. Now this one will actually work out pretty nicely for us in terms of the numbers. Initially it looks a little weird. What I'm going to first do here is multiply these terms out on the left. That will give me this. Okay, then I've got my stuff on the right. Okay, I'm going to multiply this stuff out on the right here. Then I've got this. Okay, now I'm going to move everything to the right-hand side to set up my quadratic expression. So first of all, I've got the 1/2 kx squared. Okay, now, this guy here is in terms of x. This guy here is in terms of x. I'm going to move this to the other side and add it to this. That will give me this. Take a look at that carefully. I said originally this looks a little strange. I'll take this guy here, which is negative, move it to the right-hand side, it becomes positive, add it to this term here, do a little bit of factoring. Okay, do that. Okay, then do the same thing with this term here in terms of h, and this term here in terms of h. Move this guy to the other side and add it to this. That will give you this. There we go. Okay, let me just double check myself, make sure of that. That's negative, it becomes positive, add it to that guy, that's good. That's negative, move it to the other side, becomes positive, add it to that guy, that looks good. Now this one here is actually nicely designed in terms of the numbers. Here's what happens, I'm going to actually write this out in terms of the numbers for a change. This is first of all 1/2 times 10,000, that's 5,000. Okay, then right here is 1,000 minus 4,000. So 1,000 minus 4,000 is negative 3,000. And then this right here is also negative 3,000 times 12 feet. So that's negative 36,000. So, and now I just plug it. So let's see. X is going to be first negative b. So positive 3,000 plus or minus square root of b squared minus 4ac all over 2a. So let me double check myself. 10 minus 4,3 times 12, 36.
Okay.
That's good. All right, let's see what we got. All right, so radical sign, 3,000 squared, 3,000 squared. Minus 4 times 5,000 times negative 36,000 equals square root of that, 27,000. All over 2 times 5 or 10,000. So, and now just finishing off, once again I'm going to toss out the negative answer here. It has no physical meaning in the problem. Just use the positive sign. So we could actually do this in our heads now. Watch how this works. 3,000 plus 27,000 is 30,000 divided by 10,000 is a total of 350.
More than double.
All right, works out nicely. So as I said earlier, with this problem and the two preceding, if you understand these three problems, then you've got a pretty good handle on the two chapters thus far. Now take a look here at the agenda board, as I mentioned earlier. There is the web assignment due at its normal time on Friday of this week at 12:20. Next exam is on the horizon, as I mentioned earlier. It's Wednesday of next week. Now on Thursday of this week, we have 2 more topics to look at for the chapter thus far. Then we will do on Monday of next week for the exam. Okay? Everything we've done, these 2 chapters, chapter 7 and 8, is basically Everything in the one expression.
Are they summer tires?
But notice how long it took me to meet us.
Diego. Diego. Are you staying for robotics? Yeah.
Plus, right, but there's some.
I don't get it. Yeah. Well, I mean, there's one tomorrow as well.
I might as well go today.
It doesn't matter. When they say change the tires, because some cars are like the GTA, they do go, even though you buy one in LA,
I hope my dad has the house.
they still have stock.
Square, our initial spring potential tree now.
What? If it went out?
No, if it was attached, if it was attached to the spring, I'll put it in one, stretch it out. We would have an initial.
Really strange.
See, like,
Brownish.
You better bet you like Spencer's. Like Spencer's in my way. So they'll just go for it.
yeah, the thing is, I just moved here.
Right. Well, then you might as well have done it. So like, you know, we shouldn't have every so hard put in like a dog into the pot,
No,
like $300. Which is that's definitely illegal. Actually,
The thing is, and there's photos in the packet.
exactly. Well, Miss Newell,
BJB tournaments are really easy marketing.
like this on the side pot,
Yeah.
like every kid in the top that's playing golf and you get together.
Or like, maybe every time you get a person, they do.
And I use calendar instead of Saturday. VIV though, so to me now.
That's a bad.
No, it's
not bad.
VIV basketball.
Mr. Shalley, are we ever gonna get one of your
The worst part is I'm not even feeling
science
good right
history
now.
lectures, or are we too far in the future yet?
Did you have a sore throat yesterday? Did you have a sore throat?
There's a few more, especially when we get really deep.
And Stephen Hawking.
That is.
We put Einstein up on this pedestal. He's there for a reason. There's a reason why we equate him with Einstein.
Hi,